We are about to dive headfirst into the wonderful world of virtual private networking. Before we jump on some labs, though, we've got to go through some theory and go see exactly what's going on with some of this new terminology, because it's going to be new to you, of course. If you haven't seen VPNs before, it's going to take you a little while to absorb it. There's nothing wrong with that. That's all part of the learning process. But if you are new to VPNs, please spend a little extra time with this video. Watch it a couple of times before you move on to the labs, because the labs will be that much more helpful that way. Speaking of theory, the first question I have, maybe the first question you have, is why we VPN in the first place. And the reason is that, the shared channels that we generally use between routers, between WANs or over our WANs, they have a major drawback. They're shared. And if something is shared, what does that mean when it comes to privacy? Privacy may not be the best. It also may not be terribly secure. So I'm sure you already see where this discussion is going. But before we proceed with that, remind me from your CCNA studies, if shared channels aren't exactly private and aren't the most secure things in the world, why do we have them? Cost, because they're cheaper. And we can't have VPNs between every endpoint in the world, but sometimes we've got routers and communications that need to be a little more private than we've got a chance to have over a shared channel. And one of the great things about these virtual private networks is that we bring the privacy to a shared channel because we're actually tunneling through the shared channel. We are digging, if you will, a secure channel or a tunnel through the shared channel. And another great thing about VPNs is that we can apply rules and policies to the virtual tunnel without applying them to the physical channel we're tunneling through. So that is a great feature of VPNs. Three more great features of them is these three features that they bring: data origin authentication, encryption, and data integrity. And I know these are awfully self-explanatory, especially the first one, but I want to draw a clear line between these three. Data origin authentication is done on the recipient end, and it allows the recipient to guarantee the source of the packet. Because we know that all kinds of nasty things could happen along that dotted line, right? That VPN. We could have a man-in-the-middle attack, and they grab some packets and they do some nastiness. So router 3's got to be able to say, okay, did this packet really come from the source IP address that's indicated on the incoming packet? Now, encryption, we know all about that. We know what's going on here. Encryption makes the contents of the packets unreadable during transmission. So even if that man-in-the-middle attack occurs or someone intercepts them in another fashion, then the packets are essentially useless to them. It's like going to the library, stealing a book, and it's written in a language you can't read. Don't steal books from the library. Integrity. Now, integrity, that is also done on the recipient's end, and that is the recipient's ability to ensure that the contents of the incoming packet were not tampered with during transmission. And basically, router 3 here is getting a packet and saying, hey, does this packet say what it said when it left the original sender? So these are three great features to have. Now, that tunnel, it just doesn't build itself. You and I have to do a little building here. And we used to use a little something called the generic routing encapsulation. I love that name. What do you want to call it? I don't know. It's pretty plain. Just call it generic. Well, it was fine for a long time, but there was just one little drawback. GRE is so generic, it does not allow for an encryption scheme. And you read that right, and you heard that right. GRE does not allow encryption, and that's a little too generic for today's world, in my humble opinion, and I'm sure you agree with me. Now, GRE's made a little bit of a comeback. We may talk about elsewhere working with IPsec, but it's definitely not working by itself. And this whopping GRE security hole is corrected by IP security, which is usually shortened to IPsec in VPN discussions and anywhere else. You're almost always going to see it just called IPsec. Now, thankfully, IPsec brings encryption and authentication to the table, and it is a combination of these three things, and I'm not presenting them to you in any particular order, but you should know what these three things are. The first one, authentication header, usually referred to as AH or IP protocol 51 or just protocol 51. I think you should know the AH and ESP numbers, because I've seen Cisco documentation and some non-Cisco VPN material that make a lot of references just to the numbers. So AH, it defines a method for authenticating and securing data. But I think there's a word missing from there. Now, authentication header, as we'll see, I've got some visuals coming up for you, but AH is literally a header. There's no encapsulating going on, which brings us to, clever segue, the encapsulating security payload, ESP IP protocol 50. Now, this defines a method for authenticating, securing, and encrypting data. Now, the Internet Key Exchange, the IKE, we're going to be working with a lot of IKE policies live here in the next couple of videos. So this is definitely one we need to know what's going on. And simply, it negotiates the security parameters and the authentication keys that are going to be in use. Let's take a few minutes here to talk about AH and ESP and compare the two. Now, AH brings perfectly good security to the table. You know, there's data origin authentication, there's optional anti-replay protection, and AH does not fully protect the IP header info, but it does protect the payload. And you'll see why it doesn't fully protect the IP header info in an illustration in just a moment. But the thing is with AH, and I repeat it here, it offers data origin authentication. It does offer integrity, but it does not bring data confidentiality, which is a huge difference when you're comparing it to ESP. Basically, AH lets us know the packet's indicated source is indeed the source. It lets us know the packet's contents were not changed during transmission, but it doesn't guarantee that somebody didn't read it along the way. So it does have that lack of data confidentiality. Now, ESP just brings everything we could ever want. Data origin authentication, data confidentiality, anti-replay protection, encrypts the data. You know, it's fantastic. So again, I'm repeating it there, but it does bring us that data confidentiality that we lack when we use authentication header. So the musical question, why would we ever use AH instead of ESP? Why would we do that? This should remind you of a discussion we had during your CSENT studies, your early CCNA work. Two protocols, one of them had a ton of features like windowing and sequence numbers, and the other one didn't have jack. And of course there I'm talking about TCP and UDP respectively. You know, UDP didn't have any of the great features that TCP had, but, you know, we use UDP every day for all kinds of things in our networks. And why did we do that? Overhead. And that is one of the reasons that you would choose AH over ESP, is that AH has much less overhead than ESP does. ESP is much more processor intensive than AH. The actual encapsulation and de-encapsulation itself, you know, is a lot of extra work for the router that it doesn't have with AH. There's another reason though. ESP requires what we call strong cryptography, and that is not available everywhere. It's certainly not available on every Cisco device or every non-Cisco device, and it's not even allowed everywhere. It's actually illegal to have certain devices that have strong cryptography in certain parts of the world. And when you start up a device that has strong cryptography, it'll actually have a warning for you beyond the usual copyright notices, that kind of thing. And it'll say, hey, there are places in the world you're not allowed to use this. And if you have any thought that you're in one of those countries or you want to check the list, here's the URL to check the list. So they're very, very careful about telling you that. But that is another reason you might have to use ESP. Now, let's go ahead, take a deep breath, because we're going to hit tunnel and transport mode here for a few minutes. And what you've got to do here is decide between these two modes whether you're running AH or ESP. Now, tunnel mode, that's our default mode. And with this mode, the entire IPsec process is transparent to the end host. Now, the VPN devices, which are the routers in our case, in our labs upcoming, they have a lot to do. Tunnel mode protects the entire packet by doing all of these things. The packet payload is encrypted. If you use ESP, you're going to see a header and a trailer attached to the original IP header and the data. And I have an illustration for you in a moment, I promise. And what we're doing there is encapsulating the original packet. That's where the E comes from in ESP. Now, if you're using AH, a header is inserted, but there's no actual encapsulation. And finally, with this mode, a new IP header is attached, and it's going to reference tunnel endpoint IP addresses. So in a way, you're disguising the original IP addresses that are in the original header by the encapsulation and also just by putting tunnel endpoint addresses on that header. Now, here's a visual that will really help you knock all that theory down. Now, ESP with tunnel mode at the top, you see we've got the header and the trailer there encapsulating the original IP header and the data payload. And you've got that new IP header on the very front. Now, AH with tunnel mode, you see the authentication header, the AH, is inserted right in front of the IP header, and there is a new IP header put on as well with the tunnel endpoint addresses. Now, ESP and AH combination with tunnel mode, you can run ESP and AH. They are not mutually exclusive. And if you do that, you see where everything is. The authentication header is put right in front of the original IP header. Then the AH, the original IP header, and the data payload are encapsulated by ESP. And then you've got that new IP header put on the very front. Whew. A lot going on there. So then finally, after all that's done, the entire IPsec protected packet is sent to the remote VPN device. And of course, that device has to unencrypt and de-encapsulate the packet and then send the original packet to its intended destination. Whew. So you can see there's a lot going on there. So that sounds like a lot of overhead. And transport mode brings us that now familiar, overhead versus protection level argument, because transport mode is going to encrypt only the IP payload. It's going to leave the IP header alone. And it's a bit of an oddity here. You will still have an outside IP header, but it's just going to be a copy of the original header. And that's whether you choose ESP or AH. And this is what we're looking at. You see ESP with transport mode. We've got the header, we got the payload, we got that encapsulated with the header and the trailer. But in the front, we have a copy of the original IP header. And with the authentication header with transport mode, the AH is put right in front of the original IP header, and then a copy of that original IP header is put on the front. So this is not as secure because you're not disguising the original IP header addresses in any way. So somebody can pick those off and start getting a little information just from there. So again, the argument here is overhead. And that's just really, that's what it comes down to. That's what it comes down to really with AH and ESP in many cases. And when it comes to tunnel and transport mode, you've got to make that decision about, overhead versus protection level. I think that is enough theory for right now. Great stuff there, and we're going to start putting some of it into action in the next couple of videos, build some IKE policies, and I'm going to give you that success checklist. I got a 5-part VPN success checklist for you that I want you to memorize, use it on the exam, and then use it in the real world, because I'll tell you, here's a real world note. Here's the thank you for making it to the end of this video. I don't mean it, that was boring, but I know it's 13 minutes of theory. I know that's a lot of theory. So here's your bonus for making it all the way through. I'll tell you the number one thing that causes problems when you're configuring VPNs at the command line the way we're going to do. It's just forgetting a step, because you've got a couple of different policies that have to be negotiated. You got to create something called a transform set. It's not that complicated. Don't let it worry you. Then you've got a crypto access list, which sounds like something you're going to write in another language, but it's the same kind of ACL that you've always written, just applied in a slightly different way. You just got a lot of stuff going on. So I'm going to give you this checklist at the beginning of the next video, or near it anyway, and when we start building it, we'll just check off one thing at a time, because when you have an organized plan to build something like a VPN, you are way ahead of somebody who just says, okay, I'll just sit down with the router and knock it out, because I guarantee you they could spend 15 minutes configuring and an hour and a half troubleshooting. With all that said, thanks for listening, and I will see you on the next video.